So MapReduce is a data processing component of Hadoop, and it attains the task of processing by distributing the processing across the cluster. Task on each node processes data present locally. This is important. So each machine in the slave node is processing data, is having data node and task tracker. So task tracker will only typically operate on the local data. MapReduce consists of two phases, map and reduce. And in between map and reduce, there is a small phase called sort and shuffle. Now, let's look at the easiest way to see what MapReduce is all about. Now, assume that we have a file that has some text and it is named as data.txt. The goal is to count the number of times each word occurs. So assuming we have this text which is, hi, how are you, where have you been these days, where can I find you, and are you there? So the required output that we are looking for is hi once, how once, are 2 times, you 4 times, and so on. In MapReduce, every input is viewed as key value pair. So in the above case, key is line number and value is the whole value of the line. So key by default is line number and value is the whole value. Now, hypothetically, this is how it works. So each line, which would be some input data, will be given to a map, and what map would do is it will count each word here. So if you see, first map takes hi, how are you, second takes where have you been these days, third where can I find you, fourth are you there. And this is how you get your output of map. After map, there is a small sort and shuffle phase where keys are actually sorted and all the values are brought together. So you see, how is 1, how is 1, r is 1, 1, u is 1, 1, 1, 1. So all the data from all the mappers is taken and it is consolidated based on the key. Later, you write this logic of adding everything. So you get this input and you give it to the reducer. The reducer simply adds all that has its value. So you see, for each v in value, sum is equal to sum plus v. And this is what you get as an output. This is your final output. This is how MapReduce works.
If the name node crashes, what happens?
Okay. Yeah, so as of now, in the existing version, there is something called as secondary name node, which will be covered. So secondary name node periodically takes the backup of name node, and as soon as name node crashes, you can restore it from the secondary name node. So there is no standby concept. You will have to make sure that you restore it again. And the one which is released right now, they have taken care of it by something, a concept called high availability, where you have two machines, two name nodes, and they are pointing to same data. And at one point, one name node is there which is active and another is passive. As soon as the active dies off, the passive takes over.
And these slave nodes, do they all have to be in the same data center or same geographic location, or can they be just about anywhere? I mean,
yeah, they can just be about anywhere.
Okay.
Because everything is IP based. So if they are able to talk to each other, everything should be good. That's it.
And they could pretty much be any platform, right? Unix, Linux.
Yeah, they can have any distribution of Linux, but they'll not be on Windows typically.
Okay.
Go ahead.
When the data is like you are saying that it copied into the 3, like the minimum times is 3, and if that all the maps are working on the same data, like if it is copied into the 3 servers or the 3, and
no, there is one original copy and 2 duplicated copies. So MapReduce is only working on the original copy all the time. Let's see how this will work. So I have 52 cards, and let's say we fire up, we write a MapReduce program, and let's say we have 4 mappers. So map 1 will take any random 13 cards. Okay, let's look at the whole process. So we will hand over these 52 cards actually let's say look at them as like, okay, 52 different files. We'll hand them over to Hadoop cluster, and what Hadoop cluster will do is, let's say it will break them to blocks and perform the operations. So hypothetically, let's say we have 4 blocks of 13 cards each, and we will have 4 mappers. So mapper 1 will have 13 random cards. Mapper 2 has random 13 cards. And mapper 4 has random 13 cards. Now in their map phase, their only visibility is these 13 cards. So mapper 1 only cares about his 13 cards. He doesn't care about what mapper 2, mapper 3, mapper 4 have. Absolutely. Okay. And now this mapper operates on this 13 cards, and it takes one key value pair at a time. So it takes one card at a time and comes up with heart comma 1, heart comma 1, heart comma 1, spade comma 1, spade comma 1, spade comma 1, spade comma 1, diamond comma 1, diamond comma 1, club comma 1, club comma 1, club comma 1. So like this, each guy would come with his own set of data, and this is where your map phase completes. So now all mappers will have their own respective values for this. Then you have a big sort and shuffle phase. Now what happens exactly in sort and shuffle is all the keys are brought together. All the keys are brought together. So we have sort and shuffle. After sort and, so basically from all mappers, the data starts traveling to the sort and shuffle phase, can be at one machine. And finally what we typically get from sort and shuffle phase is club 1, 1, 1, 1, 1, 1, 1, 1, 13 times. Then you have spade 1, 1, 1, 1, 13 times. After all these 4 keys are ready, because there are 4 different shades, we'll have 4 different keys, the reducer starts its job. In reducer, we have decided to aggregate. And in reducer, what we'll do is we'll take one key and all values for that key. So then this is what we end up getting. Add them and you get club, 13, spade, 13, and so on. This is how MapReduce typically works, where the map phase only concentrates on its own individual data. Then there is a sort and shuffle phase where all the data from all the maps is given to a phase called sort and shuffle. Then all the data is basically sorted based on the keys. So you'll have key and all the values for that key in a sorted order. Then the data is given to reducer, each key and all the values for that one at a time, and you finally get your output. So when we say it's a cluster of machines, assuming that this was machine number 1. Now Once you have all these 4 machines, each machine will have its own data here, the way you have it here.
Right.
Okay, so we'll not get into it, but let's say all of them have. Now the point is, see, every guy has done his individual job,
Right.
right?
Right.
Now you need some way to combine the output, right?
Okay.
So basically, we can combine output only at one place, okay? And that is decided by Hadoop which machine will do it. Let's say in this case, Hadoop says machine 3 will perform sort and shuffle. So now map 1, machine 1 will give its output to machine 3, correct? Machine 2 will give output to machine 3, machine 3 has its output, and machine 4 also has its output.
Okay.
Machine 4 gives the output to machine 3. When all the output is given, all the intermediate data is given to sort and shuffle, all it does is it figures out the different keys. So if you see how many type of shapes are there? 4, right? So how many unique keys are there? There are 4 unique keys, right? Club, spade, diamond, and heart, right? Exactly. But the important part is this. Here aggregation has to be performed. This is decided by the developer.
Right.
Okay. Yeah. So this you will have to explicitly say that, hey, you know what? I want to aggregate what I get out of it.
Sure. Okay. Okay. Okay.
Okay.
Okay.
The reducer can be any program actually. What you want?
It is your program. It is hardcore. So map is hardcore business logic and reducer is hardcore business logic. Everything else is a skeleton that is defined by MapReduce already.
Okay.
So tomorrow, let's say we had a different program where you wanted to find all the words that are occurring more than once. So you may go for the same logic, but instead of aggregating, you will see anything that is occurring twice, you put it in a separate bucket, right? So that time you will not be aggregating, you might be doing something like a filtering. Got the point?
Right. So, like, for a typical Java programmer or something, you probably have to decide on what actually you want to do on the mapping and what actually you want to do on the probably
Absolutely.
on the aggregate side, and then actually you have to think your the whole thing in that paradigm right now.
Exactly.
Okay.
You are just hitting it on the head exactly the way it is. And as I said, MapReduce, the challenging part isn't writing the code.
Right.
Expressing all the problems in a distributed fashion is a real challenge. And that's why, Hadoop is considered to be complex, because every problem so far you've been seeing in a monolithic way, you'll have to change your paradigm and start thinking in a distributed way.
Right.
Got it?
Okay. That makes sense.
And I have a question on the block size. So what determines your block size and your machine mapping? Your block size to your slave node mapping. I mean, how would you decide how big your block has to be, or how many blocks your data set is comprised of?
Okay, so the idea is this. Typically, when you install Hadoop, you'll be having 64 MB. And you can increase it to 128 MB. Now these are 2 block sizes that are typically used, and as far as the mapping is concerned, it's random. So what happens is name node, now slave nodes, once they are up, they start sending what you call heartbeats to name node, where they send stuff like configuration information and how much storage space I have and all, and then name node decides which block should go to which machine.
Okay. So see, in this case, 52 cards. So who decided that we were going to split it into 4 parts?
Oh, as I said, it was hypothetical, if you see. Okay. So how it works is, let's say you have a file of 640 MB, right? So each block is 64 MB, right?
Yeah.
So then it automatically divides into 10 blocks and spreads it across the cluster.
Each machine will have equal number of blocks always?
That's the effort that Hadoop would make. But if you have machines in which one of the hard disk is really less, then that particular thing will get disturbed. You're getting the point. So Hadoop tries to get there that way. So for example, you have 2 node clusters. So that means there are, let's say you have 2 data nodes. It's a 3-node cluster and you have 2 data nodes, and you are writing a file which is 300 MB. That is 5 blocks. Correct?
Yep.
So 64 plus 64 plus 64 plus 64 plus 44, right? If I hope my maths is right. I was a
Yeah.
maths failure. Mistakes, please forgive me. All right. So this is how your 5 blocks will look like. Now, if you take 5 blocks, replicate it 3 times. So totally how many blocks? Correct?
Mm-hmm.
Now I have 2 data nodes. Now Hadoop may, if both the machines have same configuration of disk space and everything, Hadoop may put 7 on one and 8 on another. It will do that way only. There's no other option. So basically it tries to have equilibrium, but it is all abstracted from the user. As an admin or a user, you are never going to get into those details at all, because there is something called a balancer. So assuming now that the real challenge starts here, okay, so far it is good. Assume suddenly you get more money from your manager and company and you want to have 10 nodes and you are so far having 15 blocks only, okay. Now you will run a utility, or Hadoop at times internally runs it, it's called as balancer. So what balancer will do is it figures out that okay, 2 machines have this many, other 8 data nodes are having 0 blocks. Then it will start spreading it, and then you may have few machines with 1 block and few with 2 blocks. Getting the point?
Mm-hmm.
Yeah. So that's how, but that's an internal process basically.
Okay. You know, I didn't understand where the 15 blocks came from. You had 5, and then what is the 3 times 3?
Replication.
Okay.
We spoke about replication, right?
Right.
In this case, but you said 2 data nodes, so where did the 3 come from? Sorry if I'm not getting it.
No.
Okay.
See, if you go back to this thing, so everything that you write in Hadoop, okay,
Yeah.
It replicates it by default 3 times, so that if one node goes down, other will take care.
Right. Actually, if let us say you have a mapper, and from there actually it kind of send you to 3 different nodes or 4 different nodes.
Correct.
So at any given point, is that the only job actually that machine can do, or can it actually? I mean, is it like a parallel? At the same time, it can also accept on the.
Yes, as a cluster you can run multiple jobs provided they are not on the same data.
Oh, okay. That's
because that file then gets locked. That's about it. Yeah.
Kabir.
I hope the cards example would give you some idea of how exactly MapReduce works. And this is how typically the real challenge for developers today is not really Java code or something. The real challenge would be how do you express something that's so monolithic and distributed so that you can spin it on 100 machines and get your job done.
When you said like it gets replicated to each node, it's kind of distributing the blocks. So in that case, how it's again against the capacity of that each node, right? So how that capacity is kind of handling that many blocks? We are distributing the data set, right? So let's say like if you go back to your example, last example. We have like you distributed like 13 each block, like each block will have 13 whatever, and so each block will be, each data node will be having some kind of capacity.
Correct.
Right. It's not like that whatever the capacity. So, and we are just distributing the same, like we are multiplying the blocks into 3.
Correct.
And each data node will have 3 blocks. Same kind of data set. So how that capacity is getting adjusted, and is it kind of same whatever the capacity name node will have? It will be having same capacity.
Oh, no, that you purely decide by yourself. So see, name node is the brain. Okay.
Mm-hmm.
So it does not require lot of disk space,
right,
but requires lot of RAM. Data node on the other side requires lot of disk and good amount of RAM because you are running programs also. Okay, it requires lot of disk. Okay, but this disk capacity is decided by administrator, purely administrator. So even if I give you 4 terabyte of hard disk, admin can decide to use only 5% of it for. So as I said that, see, when I was talking about disk space being ununiform or being a factor, the reason is administrator can decide out of my hard disk how much am I going to devote to what you call Hadoop, and based on that your blocks would get replicated.
Yeah. And again, the 64 MB block size is too small actually, even if it's get replicated, right?
No. That is correct. The idea is this, okay? Assuming in this case, 64 MB is a small thing, that's not a problem. The problem is, the question was, are the blocks evenly distributed or not?
Okay.
So Hadoop tries to make sure that it is evenly distributed, but if not, it comes down to how much space it is there. So it is about evenness of distributing blocks. We have 30 blocks, we have 3 machines, correct? Will it always be the case that all 3 machines will have 10 blocks? Well, you cannot always say that. So this is MapReduce. If you look at the whole flow, this is how this whole flow works. So user provides data and program, name node gets into act, and data migration starts. Data is broken into blocks of 64 MB or 128 MB. The data blocks are spread across the cluster. Once your data is in, then your job tracker gets into act and schedules the task on the task tracker. Each key value pair is processed in map phase, and then you have your reduce phase. If everything is good, we are good. If not, we get an error. That's how we are done here.